Hi, and welcome again to my Physics Online Video Lecture Supplement series. In today's video, I'm going to be continuing the set of lectures covering DC circuits. And what's happening in today's lecture is that I want to look at some applications of DC circuits, including, among other things, combinations of resistor and capacitors, sometimes called an RC circuit. I also want to look at how a few DC instruments like the voltmeter and the ammeter can be designed and constructed. And then last but not least, we'll see about maybe doing some biomedical applications of DC circuits. And that'll be if there's time at the end of the lecture. What you see in this diagram, by the way, is maybe you call it a foreshadowing, if you will, of what I want to talk about late in the lecture. Namely, here is a neurotransmitter, and what you see is, it's a pair of synapses, and what you see is some neurotransmitters passing between the two synapses. And I should say here before moving on that oftentimes this is popularly depicted as if there's sort of an electrical spark jumping from one to the other. And that is actually an incorrect depiction. What you see here is actually some neurotransmitters moving from one to the other. So we'll see if we can get to that at the end. I want to start though with RC circuits. And what an RC circuit is it's basically a resistor and a capacitor which are in series with each other. The two may be set up so that the capacitor is charged through a resistor. In other words, there's a battery and it is connected in series to both the capacitor and the resistor. Or it could be set up so that the capacitor is discharging through a resistor, meaning keep the same circuit but now remove the battery and throw a switch so that you don't include the battery in it. And basically what we're going to look at is as the capacitor is charging, the voltage across it and the charge on it, on each plate of it, would be increasing. And according to Ohm's law and according to the Kirchhoff's voltage rule, or the Kirchhoff loop rule, if you will, any other elements which are in series with that capacitor must therefore experience a decrease in voltage drop across them. And on the other hand, as the capacitor is discharging, the voltage across it is decreasing, and that voltage drop ends up being the voltage drop for all the other elements, again in accordance with Kirchhoff's loop rule. And so as the voltage drops across the capacitor, the voltage drops across everything else in the circuit, and so the current is decreased. So I want to look at all that in just a little more detail. We'll start with how a capacitor is charged and how to model the charging of a capacitor. What you see here to the right is a simple circuit for charging a capacitor. By the way, this right here is a switch, so if we switch it, basically this part of it that's in contact with A will switch to being in contact with B, and so the loop no longer has a battery in it. The loop will just be this part. Right now the loop is around like this, and you don't really get current flowing to B. In any case, what happens is that as the capacitor is charging, we can apply Kirchhoff's loop rule for this loop from battery through the switch to the capacitor through the resistor back to the battery. And Kirchhoff's loop rule basically says that the EMF from this battery, and again we're going to assume that this is an ideal battery, or we could alternatively assume that the internal resistance is included with this resistance R. Kirchhoff's loop rule gives that this EMF minus the voltage drop across the capacitor minus the voltage drop across the resistor must be zero. Basically what that means is that the current flowing through this resistor times the resistance value is the voltage drop across the resistor. The charge stored on each plate of the capacitor divided by the capacitance gives the voltage drop. So this is what Kirchhoff's loop rule ends up looking like. We can describe the charge on the capacitor while the capacitor is being charged by the battery by an equation that looks like this. QC of t, this is the total charge as a function of time on the capacitor, is the maximum charge times 1 minus e to the negative t over tau. So where do each of these terms come from? Well, the tau is called the RC time constant, is the product of the resistance R of the resistor and the capacitance C of the capacitor. This resistance R must also include the internal resistance of the battery. So that's where the tau comes from. Q max is the maximum amount of charge that can be stored on each plate of this capacitor when being charged by this battery. So what is Q max actually equal to? Well, it's equal to the capacitance times the EMF of the battery. So we basically would use C times epsilon to get Q max. And again, we're counting the internal resistance of this battery as part of this resistance R, and therefore adjusting the effective EMF to represent the voltage across the battery. If we wanted to plot that, we could either plot it in terms of charge or more realistically in terms of the voltage drop across the capacitor. So it's actually useful to have in our mind what the voltage drop across the capacitor while it's charging looks like. And since the capacitance is Q over delta V, the capacitance of the capacitor is the charge divided by the voltage drop across the capacitor. What this means is that the voltage drop across the capacitor is whatever the maximum possible voltage drop is for the configuration times 1 minus e to the negative t over tau. So tau still retains the same definition as before, still RC. V max now is the maximum voltage that this thing is going to have across it. Well, the maximum voltage that this thing is going to have across it is basically the terminal voltage of this battery. So if you were doing this experimentally in the lab, that's what you're actually likely going to be measuring, is the voltage drop across the capacitor. And you expect something that looks like this. It's basically an exponential rise, but it's an exponential rise in the sense of a negative exponent. 1 minus e to the negative t over RC. In a sense, it's an exponential decay, but it's increasing rather than decreasing. And you can see for each increment of tau equals RC, the total voltage across, and actually the total charge stored on the capacitor, increases, but it doesn't increase by as much each time. So the first period of tau, you get basically 0.632 times whatever the EMF is, or the Vmax. Then for the next one, you get 1 minus e to the negative 2, and then you get 1 minus e to the negative 3, and 1 minus e to the negative 4, and so on. So it approaches but never quite reaches Vmax. When the switch is moved over from position A to position B, the battery is no longer connected across this capacitor. So that means that the capacitor is no longer going to be charging, but rather the capacitor is allowed to now discharge. Basically, what Kirchhoff's loop rule is going to give us now is that the voltage across the capacitor and the voltage across the resistor should now, in fact, be equal. Equal drops, but in opposite directions. What we do is we say that negative Q over C, that's the voltage drop across the capacitor, plus I of t, the current, times R is 0. The charge on the capacitor, as the capacitor is discharging through the resistor, looks like an exponential decay. Q max e to the negative t over tau, or Q max e to the negative t over RC, because tau is still RC. Q max in this case represents the initial charge on each plate of the capacitor. And again, if you were doing this in the lab, you'd actually be measuring voltage drop across this capacitor. And so you use Vmax times e to the negative t over tau, where Vmax is the initial voltage drop across the capacitor. Again, you get an exponential decay. So it's worth here looking at a few short examples of charging and or discharging through resistors of a capacitor. So the first question is, what is the discharging time constant for this RC circuit? And it's a discharging time constant. That means that it's configured this way. So this capacitor discharges through this pair of resistors. So we should redraw the circuit without the switch and the battery and the other resistor, because those are kind of distractions for the discharging case. This right here is of course equivalent to having a capacitor with a 1 farad capacitance that discharges across a single resistor with the equivalent series resistance to these two. R equals 3 ohms. So tau is equal to RC is going to be equal to 3 ohms times 1 farad. And so that's actually 3 seconds. So that's what the time constant is. All right. The second question in this set of examples basically says, suppose that the initial voltage on the capacitor is 6 volts. And what we want to know is, what's the initial current through this 2 ohm resistor? So V on the capacitor has to be equal to V through resistor 1 plus V through resistor 2. And that therefore has to be equal to current through 1 times resistance of 1 plus current through 2 times resistance of 2. And since they're in series, I1 and I2 are actually equal. So I1 equals I2 equals I, because they are in series. So therefore I must be VC divided by R1 plus R2. And so that is, in this case, we're talking initial current, so we can in fact use a subscript I for initial, and the equation is otherwise unchanged. 6.0 volts divided by 3 ohms, because it's 2 ohms plus 1 ohm. And so that gives us 2 volts per ohm, or 2 amps. So that's what our initial current is through each of the 2 resistors, and total through the resistors. All right. Last but not least, we're told that the initial voltage here is V max is 6.0 volts. Again, it's discharging, and what we want is the current through and the potential drop across this resistor after both 1 second and 2 seconds. So again, we've already found that the initial current would be 6 volts over 3 ohms, or 2 amps, at time 0. So the voltage, the way the voltage works is that this voltage drop will equal this pair of voltage drops. So V discharging for the capacitor is V1 plus V2, and that's true at all times. But this is in turn equal to whatever the maximum voltage is times e to the negative t over tau. Again, we found that tau is 3 seconds. So basically what happens is we now can plug in some numbers here. V at 1 second is going to be V max, or 6 volts, times e to the negative t, in other words 1 second, divided by tau. So we'd have 6.0 volts times e to the negative 1 second over 3 seconds. So we throw this guy into our calculator and we get 6 times the basically e to the power of negative 1/3, and according to my calculator that's 4.299, so maybe we should round that to about 4.3 volts. So that's what the voltage drop across this pair must be. So if I want the current through the 2 ohm resistor, I basically use the total resistance and I use the total voltage. So 4.3 volts divided by 3 ohms, and what that gives me is basically 1.43, or if we round off to 2 significant figures, 1.4 amps. And then after 2 seconds, the voltage drop becomes 6.0 volts times e to the negative 2 seconds over 3 seconds. And so that gives us a total voltage drop of about 3.0805. So we'll round that to 3.1 volts. And so the current through the resistor now would be 3.1 volts divided by 3 ohms. And so that is approximately 1.02, so 1.0 amps. So let's, now that we've worked a few simple problems and seen the basic equations describing the charging time and discharging time of a capacitor, let's look at a few simple applications for all this. And the first application I wanted to look at is the pacemaker. So if you look at the heart, and here is a sort of cartoon of the heart, you can treat it as a natural pacemaker electrical system. It basically has its own built-in electrical system that works in the same way as our artificial pacemakers do. And basically what happens is you have a sinoatrial node and you have an atrioventricle node. And these are located here in our right atrium. And the SA node sends out an electrical signal which is going to pass through the AV node into the lower chambers of the heart down here, the ventricles. And as you know, if you hit a muscle with an electrical impulse, the muscle tends to contract. You know this because if you've ever been shocked either by static electricity or an electrical fence or a taser or cattle prod or whatever, a shorted out appliance, you know that the reaction is that you tend to contract. That's why you're told, if you ever do like a electrical safety class, that it's a bad idea to ever try to grab onto a hot electrical wire. And similarly, it's why it's a bad idea if you see somebody being shocked by an outlet plug or what have you, to just grab them to try to pull them away, because then you'll have your finger muscles contract, holding on to them, and the shock will continue, and now you're both getting shocked. And there's nothing you can do to let go. So anyway, this electrical impulse causes your heart muscle to contract. What happens is you can have your heart beating too slowly because of whatever natural causes. And so this is called bradycardia. And what happens is, because your heart is beating too slowly, you're not getting adequate blood flow through your body. So the doctors install an artificial pacemaker. And what it does is it has a battery inside, and it has a capacitor and a resistor which act as a timing element. And then there's a little electrode that they basically pass through this vein into your heart, basically to where your AV node should be, and sort of replaces the functioning of the SA and AV nodes and sends electrical discharges through this little wire into your heart. And the pulse rate is going to depend upon the values of the resistance and the capacitance of this pacemaker. Basically, you charge up to a certain level, and then you discharge. Then you charge up to a certain voltage, a certain charge on the capacitor, and then you discharge. And so, because tau is equal to RC, by adjusting the capacitance and adjusting the resistance, you can affect what the timing rate is. Incidentally, by adjusting the capacitance, you also adjust what the total charge is going to be on this. So there's a little more engineering to this than just saying, oh, pick a random value of R and C. You need to have C such that you get the right amount of charge, and then you can adjust R to get the right timing for the charge. So our next couple of applications are creatively named the Voltmeter and the Ammeter. What they are is they're devices that can be used to measure respectively the voltage drop across the circuit element and the current through a circuit element. So let's start with the voltmeter. And basically, you typically represent a voltmeter by putting a V with a circle in it in circuit diagrams. And it actually consists of a pair of resistances and a galvanometer. And what basically happens is you place the voltmeter in parallel with the element that you want to measure the voltage drop across. So maybe here's your resistor, here's your voltmeter. This is measuring the voltage across just this resistor because it's only in parallel with this resistor. And you get that from noting the fact that according to the conservation of energy, the voltage drop across each branch of a circuit must be the same. So this voltage drop across this device and the voltage drop across this resistor must also be the same. And it's worth noting here that based on Kirchhoff's rules and our discussion for DC circuits, we can figure out something about the internal properties of the voltmeter. It's making use of a galvanometer. And so what a galvanometer does is it has the deflection of a current carrying wire in a magnetic field to measure just how much current is in the wire. So we'll talk more in depth about that when we talk about magnetic fields in another lecture or two. Lecture set or two, I should say. And the other thing is that because it's dealing with the deflection of a current carrying wire, what's happening is that when you stick this voltmeter in parallel with this resistor, you're going to end up pulling a tiny amount at least of the current out of the circuit to go to this voltmeter. And ideally, you'd be able to get the measurement without pulling any current out, but of course you have to have some current in order to make the measurement to begin with. So what happens is that you pick a very large internal resistance for this voltmeter, which means that the voltage drop for both of these is going to be the same, but this is going to have a very small amount of the current because it's got a very large resistance compared to all the other resistors that it's placed in parallel with. And so basically you end up having this galvanometer. There's a little wire. It deflects in the presence of a magnetic field with a current through it. It reads off. In an analog sense, it'll read off a current, and then you figure out, okay, there's some current through the internal resistance plus the large resistor that you've placed in series with it of the galvanometer. So that current times this resistance gives you what the voltage drop must be. So that's how you measure voltage. The ammeter, on the other hand, measures the current through a circuit or through the elements of a circuit. We represent it with a little A inside of a circle. Whereas the voltmeter was placed in series with the object that you wanted to measure, whereas the voltmeter was placed in parallel with the object that you wanted to measure for, the ammeter needs to be placed in series. And the reason for that is that when you have elements of a circuit that are in series with each other, the current through all those elements should be equal. So this means that if you're trying to measure the current through resistor R1, if you place the ammeter here, you get a current that goes through the ammeter, R1, R2, and the internal resistance. It's the same current for all four of these elements. So the ammeter is going to have the same current in this case, or same current reading, as is the current that actually flows through each of these resistors in turn. And once again, you can figure out how the ammeter should be set up. You basically want to use, again, a galvanometer. And in this case, you want to have the smallest possible internal resistance of the ammeter because you want to not lower the current or have much of a voltage drop across this element. You don't want to affect the current through these elements any more than you have to by taking a measurement. And so once again, with the voltmeter, you need to have a large internal resistance, and it's got to be placed in parallel with the element you're measuring. With the ammeter, you want a small internal resistance, and it's placed in series with the elements that you're measuring. Again, the reason why this is that the ammeter and voltmeter have internal resistance, and so the total resistance of the circuit is going to be changed. And so you have to analyze the resistance of the meter as part of the circuit, placing it in parallel or in series as appropriate. So if it's a voltmeter, you're placing the resistance in parallel with whatever elements in the circuit. If it's an ammeter, it's in series with whatever elements in the circuit. You basically want it, in either case, to have the minimum possible effect on the total resistance of the circuit. So therefore, a large internal resistance for a voltmeter and a small internal resistance for an ammeter are needed. The next device that I want to discuss is what's called a Wheatstone Bridge. So previously I discussed the voltmeter and the ammeter. Both are DC devices, or could be used in DC devices, to measure voltage and current. So the other kind of thing that we could measure is resistance, and that's what a Wheatstone Bridge is for. So the basic idea is that you have some unknown resistor Rx. You have a resistor of variable resistance R3, and you have two resistors of fixed known resistance R1 and R2. And you place R3 and Rx in series so that the variable resistance and the unknown are sort of in series together, and those are in parallel with the series combination R1 and R2. Then you create a bridge, and the bridge consists of the galvanometer, which has some internal resistance. that you place connected so that it runs from point B to point D. So let's see how currents would be able to run through this circuit. Note that there's a switch here, so you can have this already placed as long as the switch is open. With the switch open, you get current flowing in through junction A, and the current splits between I2 and I1. So I1 runs through R1, R2, and I2 runs through R3, Rx. And the voltage drop R3, Rx and the voltage drop R1, R2 must be equal when this is open, because R3, Rx and R1, R2 are actually in parallel with each other when this bridge is gone. But if you put the bridge in, then it gets a little more complex, because hypothetically you could have current that runs this way around the loop to junction C. You could have current that runs this way around the loop to junction C, in other words ADC, ABC. But you could also have current that runs, for example, A, B, D, C, or alternatively A, D, B, C. In other words, you could hypothetically have a current running from B to D. In fact, if the potential is different at B than at D, then there will be a current from B to D or from D to B. If there's a voltage drop from point B to point D, there will be a current. So the way that this Wheatstone Bridge works is by eliminating this voltage drop and eliminating this current. What the galvanometer does is, if there is a current, the needle in the galvanometer will deflect. Not only does it deflect with a magnitude, it actually deflects with a direction of the current. So you can tell whether you have current moving from B to D or from D to B. And that basically gives you a hint as to whether you should make R3 larger or smaller. In any case, what you need is that delta V across AB and across AD are equal. So the voltage drop from A to D and the voltage drop from A to B must be equal in order for there to be no voltage drop from B to D, because the voltage drop across AC is the same whether you go through this branch or whether you go through this branch, or whether you go through this branch across the bridge. The only way in order to ensure that there's no current through this bridge is then for the voltage drop to be zero, and that happens in the case where I1 R2 and I2 Rx are equal. That would be the current through this resistor times this resistance, and the current through the unknown resistor times this resistance. And so you can solve all of this, and you'll find that Rx is equal to R3 times R2. So here's R3, here's R2, divided by R1. So these two have known resistances. This has a known but variable resistance. You change this resistor until you get no deflection for the galvanometer, and then you have now the resistance of this entire bridge. Yet another interesting device which is used for DC is called a transducer. What a transducer does is it converts between types of energy. Specifically, we use these to convert between electrical energy and, for example, mechanical energy, or one type of mechanical energy being sound waves. So we can get from sound to electrical signal, or from electrical signal to sound. That would be a microphone on the one hand or a loudspeaker on the other. Another use of it is to build what's called a strain gauge. And what that does is it uses an increase in resistance which occurs when a wire is stretched. So you can see a little strain wire that's wrapped around a bunch of insulating posts. And basically, if some strain is placed on this wire, it stretches, and that means that the area decreases, which drives the resistance up, and the length increases, which also drives the resistance up. And so this is all attached then to a membrane which can expand or contract with pressure changes. And so when it expands or contracts, it places a strain or releases strain on the wire, and therefore you get different resistance in the wire, and therefore you can measure just how much strain has been placed on the membrane. It allows you to measure pressure, for example. So how do you build a microphone, or how do you make a transducer for that matter? This right here is a basic diagram showing the microphone. This type of microphone is called a capacitor or sometimes a condenser microphone. And what happens is that you have a parallel plate capacitor. That would be this blue guy. And you can see there's a voltage source, there's a resistor that you can charge the capacitor through, and then there's an output. And this basically functions as the pair of parallel plates on the capacitor. So if you redrew this as just a circuit diagram, basically it would look something like this. Here's your voltage source. Your voltage source is connected through some sort of a resistor. That's connected through some sort of a capacitor. And that's basically what you have. There's some charge, therefore, on each of these two plates of the capacitor. And as you know, the capacitance is kappa, the dielectric constant for whatever's between the two plates, times epsilon naught, the permittivity of free space, times effectively the area of the capacitor divided by the distance between them. Now the area maybe is a little complex if you have two plates of different size, but you can still come up with something that represents the area term, and once you've calculated it, it's effectively constant. If you apply a sound wave to this, however, it's going to vibrate this membrane. In other words, these two plates are going to get closer together, and then they're going to get farther apart, and then they're going to get closer together, and then they're going to get farther apart. So that means that the capacitance is going to be changing. And since the voltage drop has to be basically the same because of this voltage source, that basically means that you're going to have charge flowing in and charge flowing out of this capacitor. And so the charge flowing in and out would be a current, and that basically is your signal. Your electrical signal is the current generated from the vibration of this thing and the change of charge on the two plates. And now that you have your electrical signal, now you've built a microphone. You speak in through, you're speaking out here, that's sound waves, it's vibrating this plate that generates a signal which then is interpreted as, for example, a frequency of sound. And then how large the vibration is determines how loud the sound is. This is going to determine the maximum current and minimum current. So I wanted to work a longer example. You could think of this as a proving the point, if you will. Really, it's illustrating the point of what do you choose for the internal resistances of the device that you're going to use to measure a circuit. So we'll start off with basically a voltmeter. And what we want to do is we want to measure the voltage drop across some resistor. And so the question is, when we make that measurement, how does the circuit end up changing? And then likewise, what happens if we put an ammeter into the circuit to measure current instead? So basically what happens is when you put the voltmeter in parallel with this circuit, you can draw it on looking something like this. And for all intents and purposes, the part that's really relevant to us here is that there is some internal resistance for the voltmeter. And what we want to do here is, again, we're assuming you're using this correctly, that you're not just attaching this in series. This voltage was given as 100 kilo ohms, so that's 100,000 ohms. And we're looking at a circuit that originally had a 25.0 ohm resistor here and an internal resistance of 5.0 ohms. And we're assuming that the voltage drop is really the EMF of the battery is 5.00 ohms. And so we got a 5.00 volts, that is. So we've got to figure out from this what initially is the current and voltage drop across each of these, and then what happens when we put this voltmeter in parallel with them. Alright, so this is with voltmeter. Without, we basically have something that looks more like this. So here is the internal resistance for the battery, 5.0 ohms. Again, the EMF is 5.00 volts, and we have a second resistor up here, R, of 25.0 ohms. So no voltmeter. And so maybe we'll start with this case and then we'll work through the other case and see what happens. So no voltmeter case, we have epsilon 5.00 volts. Current, of course, is epsilon divided by R plus R. So that's 5.00 volts divided by 25.0 ohms plus 5.0 ohms. So that is basically 1/6 of a volt per ohm. So the current is approximately 0.167 amps. And therefore the voltage drop, we'll call the voltage drop V sub big R. And so V sub big R must be 0.167 amps times 25.0 ohms. In other words, we're using V is equal, or delta V is equal to I times R. So plug that into your calculator, and what do you get? You get basically a total voltage drop of about 4.167. So we'll call this 4.17 volts. Okay, so that is the case with no voltmeter attached. What I want to do now is look at what happens when you have the voltmeter connected in parallel with the device that you're measuring, which is this resistor. Again, we can write that epsilon is I times R effective, but now we have to use that R effective is basically, we'll call it R prime effective plus little r. R prime effective you get by using the fact that these two are in parallel with each other. So it's 1 over R plus 1 over RV, or 1 over 1 over 25.0 ohms plus 1 over 100,000 ohms. So if you do that, you can get a value for R effective. Basically, the 1 over R effective prime is going to be about 0.04001 inverse ohms. And if you reciprocal that to get the actual effective resistance, you will get R effective prime is 24.99 375. So I'm just going to carry it to there. Okay, then to get the total R effective, you have to add this to the internal resistance, which was 5 ohms, and so you should have 29.9938 ohms. Okay, that means that you can now find what the current is. It is in fact I equals epsilon over R effective is 5.00 volts divided by 24.9938 ohms. And so the current that's drawn by this new circuit is going to be about 0.16670. So it's actually a little larger than the current up here because this was 0.1666666 repeating. So here we have 0.1667014 ... amps. So what's the actual voltage drop then going to be read as? Well, this was the total voltage drop is going to be the equivalent voltage drop for this plus the voltage drop for this. And basically what that means is that we can go back to what this R effective prime was. And so delta V, which again this is delta V sub R. Delta V sub R, which is also delta V sub V for the voltmeter, is going to be equal to epsilon divided by the total resistance here times just this resistance. So that's basically epsilon over R effective times R effective prime. Could also, of course, use that this is equal to I times R effective prime. Either way, what you're going to end up getting is, because the current is given here and the R effective prime is given above as 24.9938, what you end up getting is that this voltage drop is 4.16650 volts compared to the voltage drop above, which is actually 4.166666 repeating volts. So you can see that it's actually slightly smaller voltage drop here than here. Okay, what about when we place the ammeter in series with the resistance to measure a current through this resistor? Before we placed the voltmeter in parallel with the resistor, now we're placing the ammeter in series. So what happens in this case? Well, happily it's a lot easier to figure out all the total resistances because there's nothing in parallel. So R effective basically becomes resistance of the ammeter plus load resistance plus resistance of the battery. And so that is going to be 2.00 ohms plus 25.0 ohms plus 5.0 ohms. And so this gives us 32 ohms of effective resistance. So with 32.0 ohms of resistance, how much current is going to get drawn? Well, I should be equal to epsilon over R effective. So again, we have 5.00 volts divided by 32.0 ohms. So 5 divided by 32 gives us 0.15625. So again, you can see that this is a bit smaller of a current than what we have up here. This was 0.16 repeating. Here's 0.156. And so what's the voltage drop across just this resistor? Well, delta V sub R should be R times I. So if we multiply this by 25, we get 3.90625 volts, or 3.9 versus up here we had basically 4.2. So there is actually a significant difference in this case for both the current and the voltage drop when we place this ammeter in series with everything. So you can see where making a measurement can actually have an effect on the circuit that you're measuring. Alright, so the main new thing that we've done is basically looked at what happens when you charge or discharge a capacitor through a resistor. Most of the other stuff that we've done has been simple applications or maybe complex applications of just the DC circuits that we've already looked at. So there's not a whole lot of new terms. There are some new equations. The main new equations are that the RC time constant tau is given by the resistance times the capacitance. And then if you're charging a resistor, the charge on the resistor is given by the maximum charge times 1 minus e to the negative t over tau, and the voltage drop across the capacitor is the maximum voltage times 1 minus e to the negative t over tau, where this maximum voltage is basically the voltage of your battery, and this maximum charge is basically the charge supplied from the battery from C times EMF, the capacitance times the EMF for the battery. Similarly, if you're discharging it, you get that the charge as a function of time is the maximum charge times e to the negative t over tau. Maximum charge is the charge that the capacitor has when it begins discharging. Similarly, the voltage drop across the capacitor while it discharges is the maximum voltage drop times e to the negative t over tau. Again, this maximum voltage drop is the initial voltage drop on the capacitor. After that, most of what we did was apply circuits. So the Wheatstone Bridge we learned about is used to measure resistance. Voltmeters you connect in parallel and they measure voltage. Ammeters you connect in series and they measure current. You can build both using a galvanometer. Finally, you can make a microphone using a transducer, and transducers basically make use of RC circuits, both when building a microphone and, although I didn't show it, in building a loudspeaker. Is basically almost the exact opposite of how the microphone is set up, but that's a story for a different day. So thanks for watching today's video, because that is it for this part of the lecture, and that's really it for this set of lectures, lecture set 6. In lecture set 7, we're going to start looking at magnetism. So this is the end of just electricity, and next up we're going to have magnetism. So this is sort of an electricity and magnetism class. Therefore, you should expect to see a few lectures just on magnetic fields and magnetic force and what you can do with magnetic fields, and electricity will come back into it, of course. But that is it for today's lecture, and I guess there's quite a few credits worth here. So thanks for watching today's lecture, and look for the magnetism lecture to be put up next.